Good afternoon. We're the ODU chapter of the American Society of Naval Engineers, better known as ASNE. Our team was tasked with entering a boat into the Promoting Electrical Propulsion competition hosted by ASNE. Before we begin, let us introduce ourselves. My name is Neil St. Clair.
My name is Ryan Brooks.
My name is Alex Cartwright.
I'm Michael Jones.
My name is Kaylin Pierce.
And I am Larry Price.
The original scope of the project was to design, simulate, and build a boat worthy of winning ASNE's competition. We began by designing multiple test hulls in Inventor and SolidWorks to see which design we preferred. The data files for the hulls were then transferred to a simulation program called Maxer. We used this program to obtain crucial data necessary for future calculations, such as the power needed to reach our desired speed of 25 miles per hour. Due to complications with COVID-19, we were unable to receive funding or utilize facilities once made available to us for the building of the hull. Because of this, the physical aspect of the project has been limited to a 3D printed model. Next slide, please. The PEP program for small crafts is meant to promote educational endeavors that will grow the development of electrical propulsion while also allowing for healthy competition. Teams are granted up to $7,000 and appropriate supervision in order to design a safe boat that is fit for competition. Next slide, please. The competition was to be held in the Baltimore Harbor over a span of a weekend. The race consisted of 5 laps between a buoy at the United States Coast Guard Yard and a nearby bridge. Each lap is approximately 1 mile. The location that was selected was done so because it allows for maximum visibility. We believe that our 14-foot V-shaped aluminum hull is ideal for balancing speed and responsiveness, both of which are necessary for winning the competition. Next slide, please. This is our original timeline. It was intended for the project to take approximately 51 days, with research beginning on the 1st of April. The design was to begin 2 weeks later, all culminating in the completion of the report by the end of May. Again, due to complications stemming from COVID-19, this timetable was not possible to achieve. Next slide, please.
So there's a lot of different things you can talk about when choosing electric over fuel. And starting off, the competition was intended to explore the idea of electric over fuel because we've been such dependent on natural or non-renewable resources for a long time. So ASNE designed this race so that we could show that electric could be just as good, if not better, than fuel-powered boats. So electric power in general can be more environmentally friendly than gasoline or diesel because it doesn't create emissions like they do. And with that, you have non-renewable resources that make gasoline, and then diesel comes from gasoline. So electric can produce power without utilizing as many non-renewable resources as diesel and gasoline. Then we talk about the maintenance aspect of an electric motor versus a fuel engine. There's typically a lot less moving parts when you're thinking of maybe a piston engine. So that leads for less room for error. You don't have to worry about cracking a rod. Then with torque, electric propulsion can utilize almost instantaneous torque, much like how a Tesla uses electric motors at the wheel. That way you don't have lag. And that kind of torque being direct is essential for the ASNE race because you go full speed up to a buoy, slow down, make a full U-turn, then you have to get right back up to full speed again. Next slide, please.
Okay, so for the boat design, we decided to do 2 separate hulls, and we did one in Inventor and we did another in SolidWorks. I myself did the design in SolidWorks. Mine is a V shape. We originally agreed on 14, but for spatial reasons, in my hull, I decided a 15-foot boat would best suit my design style. Next slide, please. Okay, so this is the design process of my hull. So I first shelled with a loft the original shape, and then the method that I plan on using for putting the boat together is by welding aluminum to keep the inside hollow, cut down on the weight, cut down on the costs, largely on costs, and especially make it a lot easier for us to make a module build with what we can put inside of the boat hull. Next slide, please.
So in all these pictures is 3D printed representations of my design and Michael's design. And as you can see, there's a lot of infill on the gray boat. That boat is the one I designed, and that's because the front end is 100% solid. Like Michael just said, his boat was hollowed out to cut down on cost. So for my design, that would have to be taken care of before implementation. However, if you look to the right, you can see both boats floating very naturally in a sink.
Next slide. Okay. We did a mass properties analysis on both of our boats. I imported Ryan's into SolidWorks and did a mass properties on his. Now we can see the density, the mass, and the volume of both of the boats. This is the SolidWorks boat. The next slide will be the Inventor boat. One thing to note here would be the center of mass, and it's given to you in feet. The center of mass on my boat is directly in the middle of the X with respect to the origin. It is 1 foot below the top of the boat, so about where the passenger will be sitting, and it is almost 9.5 feet back from the origin, which is the very tip of the front of the boat. This is an ideal that we found this to be an ideal spot for the center of gravity, which leads to the boat being able to plane a lot easier, since we need the boat to get to dig. When it's accelerating, it's going to go up. The front of the boat's going to go up, and then it's going to flatten out, and the center of mass being in the back of the boat is going to allow it to dig better and get to plane a lot easier. Next slide, please.
So here's the mass properties of my design. And first off, I would like y'all to look at the mass of mine. Like I said, the front end is solid, and compared to Michael's boat, mine is much heavier. And that's also attributed to the fact that I use aluminum 6061, which is heavier than what Michael used. Also with my boat, you can see my center of mass is just a fraction off from being centered in the X coordinate. Then you have the volume difference. There's a big volume difference, most likely because of the downward keel that's on the bottom of my boat. Next slide, please.
Okay, so this is the final assembly of my drawing. It is important to note that where he opted to go for the 6061, I opted to go for the 5052 aluminum. Both are commonly used in boat metals for aluminum for their properties of strength to weight, and as well as the design of mine being welded on plates, essentially. Gives a very modular design for what we can actually put on the boat. You have the chair as the chair is bolted down to the floor, and it can be moved anywhere we want before we actually implement before we implement the screws into the bottom of the boat, and we can make sure it's comfortable for the driver, for who will ever be driving it. It's very adjustable, very modular. Nothing is set in stone, and it's built for expansion. Next slide, please. And this is a drafted image of my boat. It has all the dimensions necessary to build the boat, and we decided to give the dimensions in both feet and inches, or feet and meters. And the reason for this being is we're going to be dealing with possible international companies, and we need to know the dimensions in both, obviously, because everybody else around the world uses the metric system while we use the imperial units to measure. So in the future, that could prevent a lot of problems from happening because of the inconsistencies in our conversion factors. Right, next slide.
On the topic of motors, I had originally leaned towards using a brush DC motor for the simpler regeneration potential. However, after further delving into the depths of the internet, I was able to find a brushless DC motor of substantial size that was sold with a controller with the regeneration capabilities already baked in. However, with most of the large DC motors, they're produced in China, and weight is a logistics concern in shipping sensitive electronics across the seas. Coming in at 86 pounds, it also is a concern to our speed. However, I believe this will be outweighed by the 27 horsepower that the 20 kilowatt motor is capable of outputting. Next slide, please. Absorbed glass batteries seem to make the most sense in our use case for financial and safety purposes. Lithium iron phosphate does have a higher discharge capability. However, per weight, per discharge, per dollar doesn't seem to make much sense in a scenario such as ours. And that is before the cost of a battery monitoring system is considered. Ideally, a virgin lead acid battery would be implemented as they have a lower internal resistance, resulting in a higher discharge capability and a lower internal power dissipation, both of which are advantageous in any scenario, thusly making Odyssey, or in this case, Northstar, the most sensible brand to go to. Next slide, please.
So a new program we decided to use in our project was the Bentley MaxSurf software. Primarily, we used MaxSurf Modeler and MaxSurf Stability. With this being a brand new program that we hadn't encountered before, it was a challenge to learn how to use, and transferring files from SolidWorks and Inventor into MaxSurf proved to be difficult, as there were many translation errors in a lot of the curves of the design. I took the boat files from SolidWorks and Inventor and imported them into MaxSurf Modeler in order to be able to save them as the default MaxSurf file type, where I then opened those files in MaxSurf Stability, and given that the software is named MaxSurf Stability, the tests that it offered me was actually a hydrostatics analysis. And running the hydrostatics analysis, we discovered that there was some obvious error in the data we collected. Next slide, please. You can see that there is a massive difference in the displacements for both boats, and while the boat designs were different because one hull was hollow and one wasn't, it still doesn't make sense when you look at the data, because the boat with the hollowed out hull actually had a higher displacement than the one with the solid hull. So it was clear to us that the data gathered from MaxSurf was incorrect, and we believe that the data was a result largely of translation errors between the different programs and lack of, I guess, skill and knowledge of the program itself. Next slide.
So when designing a watercraft, a naval craft of any sort, it's important to understand the force buoyancy acting upon the object in water. Indeed, like when understanding the theory of buoyancy, an object will float if its density is less than that of the fluid that's in, and that was discovered by Archimedes many, many years back. It is fundamental to ensure that the buoyant force acting upon an object is greater than the weight acting down upon it. Otherwise, it will sink. And as you can see from the JPEG images up there, right, if the weight is greater than the buoyant force, then it's going to sink. And on the very right image, you have the inclusion of the density of the fluid, which comes into play in the next slide.
While the initial goals we set out to accomplish were not all achieved, the project was still a success. We were still able to design and select a hull to have 3D printed for diagnostics to be run. When faced with adversity, the entire team demonstrated great resolve by our ability to adapt to the ever-changing circumstances. The best example of this is how we maintained communication throughout everything. Whether that was through Google Drive, Zoom, or GroupMe, we were always able to remain in touch. By the time the next group begins the building phase, all of our calculation errors will be fixed. From there, we know the next group will do what it takes to complete the build and bring the boat to competition. On behalf of the entire team, thank you all for your time.